So I think without further ado, we can get started with the real content. And it's my pleasure to introduce Max, who's the CEO of Open Energy Transition, has a PhD in energy system modeling from the University of Edinburgh, and also at that time already started PyPSA Meets Earth, and then now Open Energy Transition. I realized I haven't introduced myself. My name is Harry van der Weijden. I'm the head of research at OET. And I'm here also together with my colleague, Tobias, who's going to speak a little bit later about his experiences. And Tobias manages the OpenStreetMap work within Open Energy Transition. So Max, over to you.
Thank you so much, Harry. Just to give a heads up, like this event was super spontaneously organized. We hope to make the best out of it. And yeah, the topic of interoperability is certainly really hot. There are several EU research projects and in general also applied projects all around the world dealing with interoperability. And like what we often get to hear is that there is an unclarity if it's if it creates a real value, or is it just a hype? And with this workshop, we are really aiming to cover a little bit the topic of interoperability, where we see challenges, how it works, what's important for it. And Tobias also talks a little bit on the robotics side, because interoperability is not new. Many people have done it in different sectors, and this is what Tobias will cover then. So yeah, just like energy planning is something special. I just want to introduce you briefly on why it is special and who is using that. Policymakers are, for example, using energy planning to design policies and regulations to meet net zero targets. We have investors using energy planning tools to guide multi-billion-dollar decision. We have system operators that use planning not to plan investments, but also to operate the infrastructure in a secure and cost-efficient way. And we have NGOs being sometimes the critical people or advocates for changes within a system. And what makes energy planning a little bit different to other sectors is that there's a really strong multiplier effect for better planning. If we can improve planning, it actually creates massive value. If you spend €1 on planning, and your impact has a factor 1,000 or more in terms of impact on investments and operations. So it's super important to make it better. And the question is then here, does actually interoperability lead to any improvements in planning? And I think if we can answer that, we can figure out if this creates value, this interoperability thing. And yeah, just to also summarize, what means actually better planning. There are multiple factors that you can consider, but in general, when we're speaking with industry and users, better planning means faster planning to create a study in much less time, better insights to make the best decisions. You want more robust insights, a higher innovation rate, new things should be adopted quickly, and there should be also an increased accessibility. With better planning could, for example, mean that you switch to an open source solution, which gives you transparency and accessibility benefits compared to proprietary alternatives. And yeah, better planning can also mean cheaper software, but yeah, I think this is really probably not the most important point, because the multiplier effect is there with planning. And actually, I would say if we can save not on the planning tools, but more on the process on the other end, like on where things are multiplied, this has much more impact. Yeah. Then what's the purpose of interoperability? I would say there are different, like we identified 3 different main purposes. One is the robustness testing. Like you can have an interoperability layer. You connect different tools. For example, Plexus is a popular energy planning tool, proprietary tool. PyPSA is an open source tool, and there are many others. And yeah, if you create with the tools like the same results, this is generally a thing that people do to just gain robustness and like more stable results. Like the tools confirm each other, which is great with, for example, convex problems, which usually should end up in like on the same magnitude of scale for the solution. And yeah, what's happening as well as a value which comes out of that is that you increase confidence in the tools, right? Like if you compare Plexus to PyPSA, both come up with the same results. This is actually a big confidence gain, and both of the tools benefit. Like I think currently the benefit, because proprietary tools are already trusted a lot, there's a strong benefit for open source tools to have this robustness testing. Another purpose that we identified is that like this interoperability part could also enable tool switching. And there are several values that come in, like faster planning. Like you can just switch to the tool that is leading to the fastest solution, right? Or has a really nice support network that allows you to accomplish your goals super fast. And I mean, here it can be, for example, if the open source adoption for your case is too slow and there's already the perfect proprietary solution, I think also thinking about going the way back from an open source to proprietary solution could be also an opportunity which would open up super easily. Another insight is that you can get better insights because like the simple reason is that you can just switch to the tools that do the job better, that can give you the insights you need. There's obviously then a higher innovation rate as well. You just switch to the most innovative solutions. Like for example, on GenX, they're working on super cool decomposition methods. So if I cannot solve my problem in one tool in PyPSA, I can just move to GenX to solve it super quickly there. There's also the increased accessibility gain. Like whoever is on unmute. Okay, perfect. Sorry for the interruption. And like there's also the increased accessibility gain. I can like switch, for example, from a proprietary solution, which has sometimes opaque ways to show something. I can swap to open source solutions, and like all the stuff is enabled through this tool switching capability. And I can also switch, of course, to more affordable tools. And the third purpose for interoperability is really that you it enables integrated planning in a super smooth way. And here again, in terms of values, you have actually like faster connections between planning domains. Like I could, for example, run my production cost model, go then into a capacity expansion tool, go then back again to the power flow tool, and so on. And if the communication layer is really stable, like this interoperability layer, I can move fast between those domains and have a eventually also even automated process to like lead to like create better results. Yeah, that's the second point. Like I can have better results because I somehow then unlocked through this interoperability all those tool connections which are usually individually applied, and I can now interlink them relatively good. And like there are more and more values in that domain as well. So better interoperability, does it mean better planning? Yes, and I would just underline this is especially the case for tool switching and the integrated energy planning case. Robustness testing is mostly useful, like if you also have robustness testing against or between open source and proprietary solutions. There's also industry interest to maintain this. And why I'm just underlining this, if we just do robustness tests between open source tools, no one wants to maintain this because there's no big value gain. And I think we saw in a lot of research projects that like they were doing this, they were doing robustness checks, but like what's the outcome of this is a nice graph that tools have differences and sometimes create the same results, but there's no real value in that. It of course increased some confidence of open source tools, but some open source tools weren't actually used in industry or somewhere. So like if they're not used, then there's no impact. And this is why I'm just underlining this point, and make sure that you create some robustness testing between open source and proprietary solutions. All right, so we talked now a little bit about the value of interoperability, and I just want to make you aware of a couple of challenges. Just keep it short here. One challenge is actually that not all those tools work with the same detail of data. And what you have to do is sometimes to apply some aggregations or simplification methods. And they generally tend to lead to information loss. And I just have one example here. That if you have a temporal aggregation case where you have hourly data, if you just aggregate it now to a daily average, then you lost all your hourly variability. And just imagine you want to go from this daily average back to any hourly signal or higher resolved signal. This is super, super difficult. And you can also have this, the same picture of simplification process, you have it also in terms of spatial aggregation, if you model a country as a node or as 10,000 nodes. In a similar way, also in terms of technological aggregation, are you considering all power system components? Are you considering switches, transformers, or is it just lines and substations? They are really going back and forth is super, super complicated. And it requires deep knowledge to actually apply this aggregation in a correct way. In the same way, if you are in an aggregated solution, now, for example, in this daily average, and you want to go back to an hourly signal, this is also super complex and usually requires some heuristics, some statistics from other parts that you apply there to come up with a feasible disaggregation approach. And that applies again to my colleague worked a lot on spatial disaggregation, Martha Fristaki. So there are definitely successful cases and it can be useful, but it's certainly not easy. And doing that right is, again, a challenge. And just to give you some sense on how it's currently this integrated planning used at the system operator level. So what we saw in general is that people start from a highly detailed production cost model. They apply some aggregation methods to run then, for example, a capacity expansion model. They disaggregate it to this original production cost model, and then eventually apply some power flow and dynamics or stability analysis to come up with a good, like, to come up with good insights to figure out if the future can be cost efficient, secure, and stable. And yeah, this is currently how it's working in the industry. Then just some recommendations. So what I want you to have as a takeaway to make interoperability successful, I think what's really, really important is to have this strong interoperability layer that you saw in the images before. This is often a many-to-one interoperability layer. So it means like PyPSA, Plex, or Sienna, all of those tools, they communicate to one neutral data standard. And this data standard should be also capable to store more data than needed, to allow flexibility, or like unknown flexibility or extendability of needs. Then second point, I think what's also really important is to focus on high impact tool connections first. Like there's no there's no need to improve interoperability of two tools which two people in the world are using. So if you want to have impact, I think you need to focus on really the most used tools like that are already today applied in the industry, where you have a big user and developer base. And like this is where you should start first, and in the best case with the fewest kind of tools available, because otherwise you end up in a huge complexity mess to make things work. And then third point, like prioritize also on this kind of interoperability between open source and proprietary tools. As I mentioned, no huge gain of open source to open source interoperability. It's also valuable, but in general, there's much more impact between open source and proprietary interoperability, because those tools, proprietary tools, are extremely widely used. Like, and if we can unlock this connection there and give people also the opportunity to run something like without paying for a server license, or to have an increased transparency gain, like open source comes with extra features, I think this connection is super valuable. And yes, sometimes it would also allow the way around, right? If you started with an open source solution, but you're unhappy with the support in the open source environment, or you're unhappy with the whole open source thing, then you can also move easily back to any of these proprietary solutions. And yeah, I guess that's super, super useful. And fourth point, when you really want to work on interoperability, there's definitely a need to work closely with tool maintainers, like people who have the deep knowledge of the tooling domain. Their knowledge is key, because like it's their daily bread and butter to change the tools and expand them. And there are also some low-hanging fruits for interoperability. And what I mean with that is, like, I know, for example, I worked on this pandapower to PyPSA interoperability. If I would add only 1-2 more components to PyPSA, I could import all the IEEE networks from pandapower, or like the pandapower networks that are accessible through the SIM standard. So like if I just have a smooth interoperability that I can create, there's huge potential that comes from them. So get maintainers involved. And you have here now I'm just handing over to Tobias, who's talking more about the experience from interoperability in the robotics world. Tobias, please.
Yeah, thank you so much, Max. So I had the pleasure actually to learn what interoperability can do to a whole software ecosystem when actually the first serious job I was starting was at a research center for DHL here in Germany. And on the next slide, you see a little bit why I consider this very similar to what we are doing here. So in this research department, we were heavily working with different kinds of robots. They have normally a problem that you need to steer them or to have a plan for them and create a plan about how they can actually be moved in a natural environment with high uncertainties. So you have normally a safety problem, you have a cost problem, not only in the price of the robot, but also in the way that you actually are going. And you have to do some, let's say it's medium-term environmental forecasts. You have to know how some other robots are moving around you or how people are moving around you. So there's some similarity between what actually energy system planning provides and what robot planning provides. If you look on the next slide, you see it's actually the robot operating system that enables us to do this software development. And the robot operating system, the first, let's say, benefit that they bring, and this is actually what they tell to people, is actually plumbing. That means it enables multiple groups in academia and also the industry with different algorithms so that they can plug together their algorithms and run them on one robot. What also was necessary is actually the tools to combine those different algorithms. And also, very importantly, the community around this. So you have to really, let's say, build a larger community around such an operating system to make it interoperable. So you have to think about, okay, what do I actually need to do this? So on the next slide, you see that a lot of people actually had the problem in the past, also in robotics, especially in academia, that when they normally they're writing a paper, they're doing a PhD, they're doing a study, they're creating a lot of code, and then they find some other open source code, and then they try to integrate it. It doesn't really work out. It is very hard to work with this code. So they at the end of their study, they release some really bad open source code they created, and then comes the next guy who actually, let's say, starts with some studying, and then he finds out, somebody else has actually been doing this. But this is too late, and there's actually, the problem is sometimes that there is no standard to avoid reinventing the wheel. It was in the past for robotic, and I think for some parts of energy planning and energy modeling, it was still the case. On the next slide, you see the success story that is actually possible if you enable young people to recombine existing open source packages so that they don't have to handle with all the problems of the different APIs, the different problems how to install them, and how to interact those projects. But if you would consider it as a Lego for robotic, or you could also think of a Lego of an energy modeling, then you can very quickly do innovation. And in our case, it was really possible with those group of people who had really no knowledge about robotics. So there was very, very little knowledge about, let's say, real life robotics and how to apply it to a machine. We could actually automate this truck that you see on the left-hand side with a software stack that actually was being developed for home assistant machines. So actually robots that help you at home. We used a lot of open source code, for example, from Google, one project called Cartographer on the bottom left corner. It's actually been used to create a map of your whole surrounding and to merge different data sets from LiDAR, camera, and radar into one big map. So a lot of different tools and packages were combined. And in our case, it was like 50 different packages that we could use from the open source world, and we added a little about, I think, 20 packages that we developed on our own, and they were all working with each other. On the next slide, you will see a little bit the architecture that such an that you will need for autonomous driving or for a robot that is actually moving in a natural environment. And it's very important to have a certain basic understanding in such a community about how do I separate those different layers in such an in such a big software blob actually that I'm creating at the end. So what is actually, let's say, part of something like seeing what is data, getting data into your software stack? What is this about? Aggregating data from different sources. How do I merge those data from different sources? And then comes also a layer that is more about mission and path planning and behavior. So what is actually mission and path planning? How do I define this so that later on somebody can say, I have created actually a new algorithm or a new software package that can be used inside of this architecture. So it's really important to have, let's say, in the community, a basic understanding, even about the wording. What does a certain layer actually mean? So there's a lot about definition. And the easiest thing that you can say is it's about, for robots, always seeing, then it comes thinking, and then it comes acting. And you can consider the same thing for energy modeling. So on the next slide, you see the package index for ROS. So it's at the moment really almost 2,000 packages that are in this index. And you know, maybe from Python or from other software ecosystems, this idea of a package. But the difference here is those packages are actually created in a way that they all can operate with each other. They can communicate with each other, and you can recombine them as if it would be Lego. And this is not something that comes by default with an open source project. You really have to think about a lot about how you can combine those tools. What's the size of the tool? What's the use case of this tool? Okay, on the next slide, you see a little bit about what's been needed that's to allow those communications called a middleware. So you have, and in ROS it's called, every application is actually a node. And you have a publisher who's actually sending an information on a standardized topic to another node that actually is subscribing those information. So in robotics, you have really real-time operating between those different software packages that might be not relevant for most energy planning tools, but it still gives you an impression. So the key idea is every message that can communicated from one application to another application needs to really be defined. So you see on the left-hand side that there's just an example for a trajectory. Okay, this is actually the way and the speed and the acceleration that a robot is following. So all those information and also the precision of this information needs to be standardized before you actually are able to plug different software packages together. On the right-hand side, you see like such a live node graph with the different topics and how they communicate with each other. This is actually a very simple example. This is really the most simplest example you can build. On the next slide, you see actually this is this is called the software architecture from Autoware. This is an autonomous driving stack that has been developed on top of ROS. And this is just 1/4 of the architecture diagram. So there's a huge amount of nodes and messages that are transported in between. And in general, you can, let's say, with the right middleware, with the right standardization, you can really build massive amounts, massive size of applications. It's actually that's a real modular architecture, you would call it. There's also this monolithic architecture that you see a lot of those kinds of software around. That is really, let's say, one application where you don't have the communication overhead. Because one thing must be clear, the smaller you actually are making those packages, the harder it will get to do the communication in between them and to do the standardization. On the next slide, you see a little bit what has been done in robotics to scale such an architecture on the example of actually a robot that's using for agriculture, for actually farming. So there is actually robots that are used there already a lot. You can see them actually in field. What they are doing is, if you want to build such an architecture, you start with simple use cases that are still scalable. That's the idea. So you start with your small farm area where there are fences, where everything is controlled. You know the environment a little bit. You know what's actually been expected, and also maybe you also know the outcome of your models a little bit because you have this studied so well. And then you increase the complexity. For example, one good idea is, for example, weather. Let's say you take for an energy model, you take an area where the weather is very predictable, very easy to understand, where there's not really hard extreme in weather, but maybe then you start going to some other areas where there's some really extreme weather conditions that you also have to consider for your energy planning. Okay, the next slide will give you a short summary about what we can learn from other domains, like robotics and the robot operating system. So modularity is really the key. You find more about modularity also with the term Unix philosophy. And one thing that I didn't mention about, and I found also very helpful actually in the team I was for this robot that we built for DHL, was the so-called mythical month problem, because sometimes if you want to have modularity allows to create smaller groups to work on one software package. So you don't have this need this very big teams to work on one software package. Now you can split them so that you have one small or multiple smaller teams to work on a software package. Another good thing is don't reinvent the wheel. It's always a bad thing to do. There's one reason not to reinvent the wheel, and this is for educational purposes, because you want to really understand how the wheel works. Sometimes you need to do this. But in most of the cases, you really need to understand what already have been done and how can you combine existing tools. Then one thing, to create such an operating system, it's called, or application layer, very important, clear agnostic standards for formats and interfaces. Language agnostic, in ROS it was Python and C++, but also support for Rust, Java, and Go. You need a certain, in this case, real operating system baseline to do this. In ROS, it was always like, use Ubuntu 2020.04, for example, because all the applications that we will provide will run on a fresh installation of this operating system. Because installing a lot of different tools in different versions sometimes, from different programming languages, can cause a lot of dependency conflicts and a lot of frustration in how to set up such a system. Then scaling or having a region that we all share and that we can all have a look at as an example region to develop such a thing could be helpful. Then you need the technical steering groups to standardize interfaces and issues, and yeah, we will need real experts. Strong community, neutral governments, and at best no conflicts of interest, that people, let's say, really want to push one thing forward just because it's their personal interest. And what I also find very important actually for the robot operating system was really a strong summer school of 1 week that was done every year at a university actually next to me. in this way, they could scale this knowledge and how to build inside of such an operating system. They could provide this knowledge for people all around the world. Okay, I think that's it. Thank you so much. Okay, we have still 20 minutes. That's good.
Yeah, so thank you very much, Tobias, and thank you, Max. There are already some questions in the chat. If you have other questions, then keep writing them. So maybe a first question from Max is what your definition of interoperability is, because we sort of started talking about it as if that had already been discussed, but how would you define interoperability for energy models?
Yeah, like, I mean, the definition of interoperability, like, you can just get it from the word already. I mean, I guess basically one tool should be able to work with another tool. And you're like, how that will look in detail, this obviously depends on how you design this interoperability. Like, it could be, for example, like you pass, let's say, PyPSA data to this interoperability layer, and then it's basically just data being accessible to then also this other tool. Yeah, or like it converts the data, the PyPSA data, into a format that is useful again for another tool. And if you achieve this, like, if those tools can then communicate with each other, then you have this interoperability, really.
Thank you. And maybe another question, and you can decide who of you wants to answer this, but Tobias gave all these examples of how this has been addressed in the robotics sector, but in energy models, we are not at that level yet, and we don't have those kinds of standards that Tobias, you said were crucial in the robotics industry. Why don't we have them? What's holding this back? Yeah,
like, I can just maybe mention the like, there are certain standards already out there. I think the SIM standard, Common Information Model, like, this is one standard, I think, mostly focusing on power flow tools, if I'm not, like, if I remember correctly.
Yes, it's the CGMES, sorry. Mm-hmm.
Yeah, so like, it certainly exists in a way already, but like, it's currently limited. For example, this whole communication between, let's say, capacity expansion and production cost models, this is not there yet. So yeah, like maybe, Tobias, do you have another thought on that?
Yeah, I think it's also a matter of money involved, and also about the complexity. I think in energy modeling, the complexity is increasing, and there's no more money involved, and it's just a matter of time, and you need a certain critical mass of people, and to bring them together to standardize such a thing. And then you need a lot of people to adapt such a standard. And I think there is now the critical mass of people. And it's like, I think also energy modeling was not that popular, or open source energy modeling was not that popular like 5 years ago. And it's like that you need certain time to standardize things with open source. It takes some time. But the open source is actually the only way to standardize the application between, or the communication between different applications. This is a very typically open source use case. And proprietary software from the past has no interest in interoperability. They want to own normally everything.
And Tobias, in your experience, what if you have different options, of course, to implement this interoperability. You could have this middleware. You could have a middle layer that communicates with all the different tools, or you can have tools directly talk to each other. How do you decide which one of these options to use?
I think to get started, I would say everyone communicates into a database is something that works. As long as you don't have bidirectional communication, and let's say that one application is really working online with another application, and there's a constant communication between them, it's totally fine to have like one model creating an output that is in a standard way that can be just been taken again by different applications. But there might be also in the future use cases where you want to have a live communication between, like TCP/IP is actually really, that's what been actually implemented for a lot of robots, that you have this bidirectional live communication. But I don't think that you will need this for the beginning. It creates a lot of complexity.
Like I think, like Tobias also mentioned something that if you really do something, you also learn something. Like this is, I think, the reason the one reason why you can reinvent the wheel. And I think in particular, like making the connections between some tools better will actually also help you understanding where's the communication issue. So I would say it's actually probably good to also do two things in parallel, like improve the one-to-one connection, just to make sure you can like remove this low-hanging fruits that I mentioned with like if you add two components to PyPSA, you have the smoothest interoperability between two tools, and like that's amazing. But from that you could also learn on how to do this like API or middle layer that we're speaking of better. And I think here we also, as I mentioned before, like start small, like start with a small, if we want to do integrated planning, start with a few tools, the fewest option as possible, like maybe 2 tools in each domain, capacity expansion, reduction costs, and power flow modeling, or something like this, and try to make them work together.
Yeah, do you have some examples of projects where this really had a big impact, this interoperability?
So, like examples where it has impact. I mean, I'm just dreaming, and if I'm dreaming of like people, and there are a lot of people complaining to be locked into some proprietary solutions. And like they want to switch to alternatives, but it's really hard for them to switch. It's this whole vendor lock-in effect. And if you allow people to switch easier, like for example to open source solution, they could unlock certain possibilities. For example, this accessibility gain that you have in open source, the gain to be more independent of developing your own features that like where you had no control in a proprietary solution and so on. So like there's clearly an impact if we could have the interoperability that is working. But yeah, I think the other interoperability use case where this is successful, I think Tobias showed the best examples on like how this just unlocked a vibrant community to actually work together.
Yeah, there's other examples. For example, Home Assistant is one great example. Also, I appreciate a lot, where you actually have a whole, let's say, base layer and a framework, and there's a lot of people actually creating plugins for this ecosystem. But I also think that the ROS example is very good because it has also the different the idea of a standardized architecture that you put on top of it, and this will enable actually a lot of new use cases to couple. You could imagine like couple actually weather models much better to an energy model. This is just one idea that just come up with me.
Okay. There's a question about validation as well. Because Max, you talked about using one model to validate the results of another model.
Yeah.
Which of course comes with the risk that you're validating two things to each other that are both not true. So in what cases would you want to do this?
Yeah, like so this whole robustness testing, as I mentioned, sometimes it's like in the best case, often we're dealing with linear problems, like in the capacity expansion case, like we should come up with the same results. Like where's this useful? I think it's really key for just creating confidence. Like some people, they don't trust a certain tool. Hey, like like in general, like if I'm using, for example, one tool and I get results out, I want to check if the other tool promising the same features is producing the same thing. If it's not producing the same thing, I really need to find out what's going wrong. And like some of those, like in some projects that we're working on, like with N2E, for example, this kind of robustness checking is super important. And here, like there are already some proprietary solutions in there, and we're just doing robustness testing between proprietary and PyPSA, for example, this open source tool. But then also, like when there are differences, and I think Antares was also tested compared to Plexus results in the past. But they had, like they identified differences. Like they saw the tools are not creating the same results, and they couldn't answer why. And like if we have then robustness testing to maybe eventually another open source tool as well, where we have full transparency of how those things work, we can do actually proper testing and finding out why things are different. And yeah, like I think here the key is really just a confidence increase that could benefit the whole user space.
Yeah, so it's not replacing validation against real data. But you still also want to validate model results if you can against measured data or other real world data. Maybe you already touched on this a little bit. So we see, of course, that the developers of proprietary tools, specifically the kind of smaller, more niche tools, are not big fans of this. To say the least, we've seen this, of course, with Plexus. I don't think we can say what these developers really want or what their opinion is. But Max, can you say something, or Tobias, about how we can get them on board, or and how far we need them?
Tobias, do you want to start?
Yeah, I think it's important to create an open forum, open space, to discuss the needs also of users, because what I've seen so far is mostly actually developers connecting on this. But you would also need some forums for users, to increase the exchange between different tools. Yeah, it's like, I think that you would need really, let's say, some community that is outside of the existing frameworks that you see, something that is a little bit more neutral.
Okay. And then getting more practical, perhaps, Tobias, do you have tips on data storage when you're transferring and adapting data from one model to another? Do you have best practices? Should you use proper SQL databases, other tools?
I only know what's been used so far in PyPSA Earth, but have like an X-array or looking into existing standard, what's already been there is always the best idea. So I think creating your own database is definitely a good idea. So it's really about using what's already there. I think this is for everything that we talk about. Every standardization, we should have a look, is there actually already an existing standard that we can just implement and reuse and just combine them maybe in a smart way? For example, I have a background in actually atmospheric physics, and there we use a lot of X-array and NetCFD. And maybe this is a good standard to use. I don't know actually if we can store every information in such a data format, but it should be considered what's already the data formats that most people are using. And what are the tools also that bring those data formats with them, because you don't want to reinvent the wheel here.
Yeah. Maybe that links to another question as well for Max. So some of these models and tools don't require a lot of computing power. Some of them very definitely do. How easy is it to implement a hybrid solution where maybe you can do some things locally, you can run some other tools on cloud, and maybe you can say a little bit about also at OET what we're working on in this space.
Yeah, I mean, certainly to run everything locally is generally feasible if you simplify a lot. So this is one thing you can always do. If some of the optimization problems just needs high performance compute power. Currently, what was annoying, for example, in open source, in the open source ecosystem, is that you need your own setup for your high performance computer, for your cluster. You need to purchase your solver, and you do the whole contracting yourself, and that can be challenging in industry and sometimes also in research. And yeah, at OET, we are currently building up some kind of service to basically get rid of this complexity. If you use some proprietary tools, you just click and they took care of this whole solver licensing and compute stuff. And this is basically what we also have relatively, actually we have it enabled in the open source space. It's something we haven't published yet fully, but it's definitely we're using it internally, and the goal is really to remove the hassle from you for this compute stuff, and eventually even save costs, because we have some solver pooling, we have some experience on benchmarking the best solvers for your problems and so on, and have a good oversight. So there's definitely work going on. We hope to announce later this year more about that. But yeah, this is really something we're using already in PyPSA. It's fully agnostic to any optimization framework. You can use it with GenX or any other thing, and there's a easy integration possible. And in general, we build things that, okay, if you don't like to work with us as an interface, you still have all the solutions, the infrastructure available that allows you to do it yourself.
Thank you. And I think with an eye on the clock, with about 30 seconds left in this webinar, I think we'll probably leave it there. There are some other questions in the chat. I think most of the questions have been answered. If your question hasn't been answered, or you want to talk more about this, then get in touch. You have email addresses here on the slide in front of you. Send us a message, and we can have a separate conversation. Or if we can help you with anything in this interoperability challenge, send us a message, and we'll see if we can collaborate to do something cool. So that's, I think, mostly it, but I'll leave Max to have the final word.
Thanks, Ari. Thanks, everybody, for listening. Just to answer the first question that we had, is interoperability hype, or is it real? Like, is it creating real value? And I think it can really create real value. And then, this is the kind of insight that we also want to share with you, and hopefully it's clicking. Thank you, everybody.